It's got negative numbers at the top, positive numbers at the bottom, but we understand that absolute magnitude stars with large negative numbers are actually quite bright. Okay? So the vertical axis looks messed up, but is not, and the horizontal axis really is messed up. Right? This graph should just be going, whoop, why don't we change it because it's too late. Okay? Notice that most stars fall on a little band, and this band is called the main sequence. And that's because it is the main sequence for the stars. Yeah. Now this lets us do, oh, here we go, yeah. So this is hot, this is cooler. Notice that I've made hot blue and cooler red. Okay. That's bright, that's dim. And now there's all sorts of good questions that we can ask, right? Like, why are these stars so bright, but they're cold? How can a cold star be bright? What's the other factor? They're big. They got a big area. That's why they're so dang bright. Yeah, there you go. They got a lot of radiative area. So Betelgeuse, I believe, is a red giant. Okay. These stars here are very hot, but they're not very bright. That's because they're small. Yeah? That's the other thing that's going on here, right? Okay. So if we're here on the main sequence and we go this way, what's happening to us? Well, we're getting hotter, but we're not getting brighter. So what has to happen to our size? We have to get smaller. What if we go this way? Or how about we go this way, right? We are getting brighter, but we're not getting hotter. So how do we do that? We're expanding, right? So red giants are stars that are puffed up because they're getting indigestion. Okay? Yeah. We have it, right? Here is another one. This is from my astronomy book. The sun falls right there. It's right, it's an averagey sort of star, right? And notice that the spectral types here are put on the bottom. This is what they do. They actually can look at the spectra of the star and tell its temperature from the spectrum. It's more precise than doing the black body radiation, the Wien's displacement, right? And the way to remember these is, oh, be a fine girl, kiss me. And I apologize, right? Oh, be a fine girl, kiss me. Yeah, sorry. But there it is. And now you can't forget it. There we go. Apparently, me is cooler, but O is hot. So, has nothing to do with the kiss. That one's worse. Yeah, yeah. Okay. So here is the star. This is a key thing, right? The stars have atmospheres, just like the Earth has an atmosphere. This stuff is all plasma, but the stuff in the atmosphere is not necessarily all plasma. Okay. It's very hot, right? But the atmosphere itself can filter the light from the star. So the star is putting out this nice black body curve, where this is wavelength and this is intensity. It's this nice little thing like this, right? And the atmosphere is filtering out spectra. So for every line, every bright line that we saw, and I think we saw this in this room, right? Didn't we have the little spectra thing, and you guys looked and you saw the bright lines? For every line of those that you see, okay, the gas can also absorb that same line. For every line it can give off, hello? Can I interrupt? Yeah. For every line that it can give off, that gas can absorb that line, right? So by looking at if we look at the spectrum of a star, the star has little lines that are removed from its black body. So this rainbow you see here, okay, that's just the hot star. Hot stars give off all frequencies because it's the energy given off by the random thermal activity of the star, right? These spectral lines are the wavelengths that are absorbed by the atmosphere of the star. Now, what can you tell by looking at the spectra of a star? We can tell what's in its atmosphere, and by telling what's in its atmosphere, we can tell how hot the star is, right? This is a key concept. Here are spectra. Obviously, these are real spectra. They're not quite as crisp as that. That was a laboratory spectrum down there. This is like from real stars. And these spectra can show lots of things. They can show redshift, which means it's moving away from us, Doppler shift, right? But they can also tell what type it is. So if you were a spectroscopist, an O-type star looks like that, and an M-type star looks like this. And it goes gradually from one to the other. But there's key things that they look for. And these correspond to particular temperatures. And you can get a PhD in this. In fact, my cousin has a PhD in this. He designs instruments for NASA space probes, right? He's one of these guys, right? This is crazy.
Can you also tell the age of the star by looking at the spectrum? Because
The age of it by the spectrum. You can tell whether it's on the main sequence. I'm not sure how you can, if you can tell how far along it is. And then it's like blah, 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 right? All these things, right? Weak hydrogen lines, spectral lines are spread out because of the thermal, the heat, right? So there's lots of that effect. And then once you get down to the M's, you don't need to know all these things, right? But once you get down to the M's, you start to actually get molecules, and the atmosphere gets so cool that you can actually get, like chemical bonds can occur, which is, there we have it, right? Okay. You can have neutral metals, so they're not even charged, right? Okay. We are a type G star, so we're the girl of, but we're before the kiss me, so. Yeah. And then they all have these little prefixes like climbing walls, and they did those backwards too. So 0 is the brightest, 9 is the dimmest. Once you start doing stuff backwards, hard to stop, right? That's just hard to, I just keep doing it, right? So this is, I have made up this great way to remember things, right? Okay? Hot stars are big, they are bright, they are brief, they don't live very long. Okay, the biggest stars with the most fuel burn it so fast, right? And they are blue. Cool stars are diminutive, which is a word that means small, dim, which means not bright, durable, which means they last a long time. See, I found these words, right? And red. Red. When you think there's like a freaking word in the English language that means red that starts with a D, Durham is a color of red, but nobody knows that. Durham? What? That's a rodent tiger. Right? Okay. So I think it's better. It's red. 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 Yeah. Why they are brief and why they are durable. Yeah. We'll talk about that next time. What exactly it is that drives that. But all right. So now you can do something called spectroscopic parallax. Parallax is in quotes because it's not parallax. Okay? It's something else. You guys are like acting like we're about to run out of time, right? So what we could do is we could look at the spectra of a star. We could determine that it is a certain type of star, and we can determine that it lies on the main sequence. We can read the graph, right? Go, okay, it's on the main sequence, so it's here. We can go over, and that's how bright it really is. This is a crappy way to do distance, by the way. It's not for careful work, but approximate work. So if it's this type of star and it appears to be, a plus 12, but it really is a 5 at 10 parsecs, we can use this formula here to calculate how far we are from the star. Okay? So if you've got a BO, sorry, that's a B0. If you've got BO, I'm just kidding. I'm joking. Okay? So if you've got a B0, so we'll do a 0 like that, right? And it's got an apparent magnitude of 8. Well, let's draw, a B0. Oh, there we go. I drew the lines already. So take 0, go up there. I go to the middle of the main sequence because it's got some width to it. Okay? What is that number? It's minus 4 point, what do we think that is? More 4.2 up there? See what I'm doing? Go up, go over, right? Isn't it 4.2? I'm going to say 4.2, right? So it's big M is minus 4.2, right? Little m is 8, and then I'm just going to use this. We want to find the distance, right? So m minus m is 5 log d over 10, right? So m minus m over 5, 10 to the, right, is d over 10. Is that right? Times 10. There we go. Ooh, that's a little